Right, seems like the trickle has died down a little bit here. So welcome to this Water Institute Water Talk. It's my great pleasure to introduce Dr. Ameli. He's coming to us from UBC, where he's part of the Department of Earth, Ocean, and Atmospheric Sciences. He's also an alumni. He did his PhD in civil engineering here at Waterloo quite a few years ago now. With me, yeah. That's not the important part. He's a Waterloo grad. So his research is at the interface of hydrology, hydrogeology, and data science, focusing on how the physical structure of landscapes governs water involvement from movement. Sorry, glasses. I should have brought my glasses. From rainfall to stream flow. He combines mechanistic models with machine learning and sensing tools to improve predictions of water availability, flood risk, and water quantity, particularly in unengaged basins. For the great work that he's done in the recent past, he was recently awarded the 2025 Canadian Geophysical Union Early Career Award, which is quite achieving. Good to hear about some of the fun things that he's up to these days.
Welcome, everyone. Okay, everything's fine here. And happy to be back at the University of Waterloo. This is where my thinking as a hydrologist has been shaped. Thanks for organizing this talk, James, Julie, and thanks for having me today. So today I talk about, probably I should be close to the source. Oh, okay. I'm okay here. Let me see if it works. No, okay, it's a battery, yeah. So today I talk about the functional reality of watersheds. So a journey toward understanding how watersheds actually function, not just how precisely we can predict their outputs. So watershed hydrologic function describe how a watershed partitions, store, and releases water. If watershed releases rainfall or snow melt in these, through these flow passes or through these flow passes. Watershed hydrologic function can be as simple as what we see on the left, where rainfall and runoff from event to event rainfall and runoff map together linearly, or can be as complex as this, where for a given rainfall volume, we can see a wide variety of runoff volume. So we can have a simple function versus complex function. But the key insight is that we still lack a generalizable framework to identify a simple or a complex watershed and understand why they are simple and determine when, where, and how simplicity breaks down and complexity arises. This understanding is important to inform the design of both models and monitoring networks. So for models, this understanding watershed hydrologic function can inform tailoring model structural complexity to watershed natural functional complexity. And for monitoring design, such information inform optimizing the monitoring network spatial and temporal distribution. Indeed, model and monitoring designs for both gauge and ungauged watershed depend on understanding the nature of the rainfall runoff behavior, and one-size-fits-all approach simply don't work. Back in 1986, James Dudge, an eminent hydrologist, actually offered this strategic insight. To develop a generalizable theory of watershed hydrologic function, we should first turn to simpler watershed, and by understanding and synthesizing why and how they behave simply, build upward to understand how complexity arises in complex watershed. This is the strategic pathway that I follow in today's talk. But what has happened since 1986? Massive advances in computational method have pushed the field of hydrology and water resources toward prediction rather than understanding and synthesizing. And unfortunately, one-size-fits-all modeling has become increasingly prevalent in hydrology. Actually, this brings me to the three questions that I talk about in today's talk. In the first part, I talk about understanding and synthesizing how prevalent are functional simplicity and complexity globally. Second, on understanding and synthesizing what drive functional simplicity and complexity. And finally, we see and evaluate how the information of watershed hydrologic function is important to identify to what extent are the most precise deep learning model functionally reliable. Oops. In the first part, our objective was to develop an empirical framework to classify the degree of functional complexity of rain-dominated gauged and ungauged watershed. The analysis that I show was conducted by my former master student, Hamed Sharif. This is our empirical framework along the gauge rain-dominated watershed. Each dots in this figure reflect the one delineated rainfall runoff event through observational data. And we conducted this classification separately for dormant and growing season. Simple watershed are those watersheds with linear event-to-event functional relationship. Indeed, single linear regression strongly map rainfall volume to storm flow or runoff volume from one event to the other. And by strongly, I mean R square or goodness of fit of larger than 75%. Intermediate watershed are those that shows segmented linear event-to-event functional relationship. And segmented linear regression strongly map rainfall volume to runoff volume, and again, strongly means R square of larger than 70%. And complex watershed are show highly nonlinear functional relationship, where for a given rainfall volume, we can have a significantly different menus and choices of runoff volume. We then expanded and scaled this classification to ungauged watershed globally. In this part, we first analyze and classify more than 4,000 gauge watershed into simple, intermediate, and complex functional behavior based on more than 2 million delineated rainfall runoff events and through the classification framework that I just showed in the previous slide. Then we train an XGBoost model to predict the known functional classes of gauge watershed using key watershed attributes such as key climatic, topographic, and geologic watershed attributes. Look at the precision and specificity of the trained XGBoost model in replicating the functional label of gauge watershed, which were set aside during model training. Those that we call them unseen watershed or test watershed. This pretty much high precision and specificity gave us the confidence to use the train XGBoost model and extrapolate the functional label to more than 77,000 ungauged watershed globally. Here is our results along the ungauged rain-dominated watershed across the globe, and red dots or orange dots reflect the complex watershed. You can see that functional complexity is widespread across global watershed. And in summary, complex watershed drain more than 87% of the ungauged land area that we studied in this study. Let's look at some regional insight. Europe, Africa, Southern Asia are pretty much complex, so we can see that the functional behavior is pretty much complex. And we have a big surprise here, and that is the Pacific Northwest of North America and Seattle, Washington area, and also Western British Columbia, which were dominantly simple. So single linear regression model can strongly show rainfall runoff behavior. We don't need like a deep learning AI model with millions of mathematical parameters. So let's get back to good insight on why simplicity and complexity arises. And in this slide, I want to actually show you how I'm using how I'm linking simple versus complex behavior to functional time variance and functional time invariance using a spectral coherency analysis between precipitation and a stream flow signal. Here, the coherence value varies between 0 and 1 and shows how the transfer function or unit hydrograph linking precipitation to a stream flow change over time. Change, for example, at the weekly scale, at the monthly scale. So high coherence indicate functional time invariance, uniform and consistent unit hydrograph from one event to event throughout the year, throughout the 40 years of data that we had. And this is the hydrograph representation of these type of systems. Precipitation pulse of type 1 always generates a stream flow response of type 1 prime. Again, precipitation pulse of type 1 generates a stream flow response of type 1 prime. This is the system with high coherence, which reflects functional time invariance. So system with high coherence indicate functional time invariance. On the other hand, system with low coherence indicate functional time variance. We can see diverse event-to-event unit hydrograph. From one rainfall runoff event to the other, unit hydrograph can significantly change, and this is the hydrograph representation of this system. Precipitation pulse of type 1 sometimes generates a stream flow response of 1 prime, sometimes generates a stream flow response of 1 second. You can see that the stream flow response to identical precipitation pulse might be very different because their unit hydrograph are very different. Once we put our classification result, classification of the simple, intermediate, complex, besides coherency value that we quantify here, we saw that simple watershed generally show very high coherence value with a median close to 0.9, and they resemble time invariant systems. And on the other hand, complex watershed show very low coherence value. So below 0.5 technically shows the system is very time variant, which means that the transfer function and unit hydrograph significantly change from one event to the other. So complex watershed show time variant behavior, simple watershed show time invariant functional behavior. This classification framework is not just theoretical, it has practical power. And in this slide, I show you how we can use this functional classification to evaluate the adequacy of long conceptual models. Here, we consider our classification results and put them beside the predictive performance of HPV conceptual hydrology model. So here on the y-axis, you can see KG along the evaluation or test set of HPV model. And once we put our classification beside this predictive performance, we saw that predictive performance of HPV model systematically decreases as the watershed degree of functional complexity increases. Long models such as HPV fail in functionally complex watershed, but might be sufficient for functionally simple watershed. So overall, this empirical finding, the empirical findings of the first section of my talk showed that most watersheds are complex and do not exhibit a stable function over time, and the long model may be inadequate to represent their time-varying, functional time-varying behavior. In the second part of the talk, let me delve deeper into the driver of this functional simplicity or time invariance and functional complexity or time variance. And I provide an example of a snow-dominated landscape here. So when we think about functional time variance, the first and major driver that comes to our mind that's controlling functional time variance and time invariance is climate variability. Here in this section, I asked, is it climate variability alone, or does landscape form set the conditions for functional time variance or time invariance? And the result that I show was conducted by my former master student, Mahmoud Tahirian, and my current PhD student, Jawad Rahmani. In this study, we asked what causes time variance in a snowmelt-drive flow paths in hill slope-dominated landscape. So what causes time variability in flow path pattern drives after a snowmelt that we may see this flow path pattern in year 1 and we see this flow path pattern in year 2. What causes this time variance in watershed hydrologic function? And our objective was to explore the interannual variation in climate, specifically in the rainfall amount that falls before the snow season. Our objective was to explore how the interannual variation in climate, specifically the rainfall amount that falls before the snow season, interact with the watershed physical structure to control year-to-year variation in snowmelt dry flow passes. Here we isolated rainfall amount in the fall season before the snowmelt season because experimental research showed that this is the key climatic factor controlling subsequent snowmelt partitioning in spring and winter in many watersheds across the US. In many critical zone observatory watersheds across US, this experimental finding was obtained that fall season rainfall strongly controls snowmelt partitioning in the subsequent months. In this study, we had two snow-dominated watersheds. The first one was Nanika watershed, a steep mountainous watershed with 22% slope and with patchy subsurface hydraulic conductivity. Here, patchy means that there was a strong lateral or horizontal heterogeneity in subsurface properties, in subsurface hydraulic conductivity or subsurface permeability. The second case study was Kirkland watershed in northern Sweden, which was a gentle watershed with 5% slope, but with horizontally or laterally uniform hydraulic conductivity or permeability. At the same time, hydraulic conductivity or permeability in this watershed was vertically layered, which was decaying exponentially and sharply with depth. So vertical pattern in conductivity, but no horizontal pattern in conductivity from one place to the other part of the watershed. Here is the methodological framework that we implemented in each watershed. So first, we use Parflow CLM EcoSlim model. It's a model very similar to HydroGeoSphere to mechanistically track the fate of a snowmelt. And of course, an extensive set of hydrometric and tracer data were used to develop and validate the model. Second, actually, we focused on two natural climate scenarios, the rainfall-rich scenario and the rainfall-poor scenario. The rainfall-rich scenario corresponds to years with high fall season rainfall, and the rainfall-poor scenario corresponds to years with low fall season rainfall. A snowpack and a snowmelt were very similar between two climate scenarios. So the only isolating factor was fall season rainfall prior to a snowmelt season, but the snowmelt and snowpack was very similar between these two scenarios. The goal was to isolate the role of antecedent rainfall prior to snow season. Third, we quantified the water phase or water flow passes. Using particle tracking, we partitioned a snowmelt into shallow flow pass, deep flow pass, long-term storage, and actual evapotranspiration. And we quantified the portion of a snowmelt that becomes each flow pass or storage in each year or in each month, as you may want to check the paper to see more about monthly and seasonal analysis. Ultimately, we quantified the temporal sensitivity of flow pass to pre-snow rainfall. How sensitive is long-term storage to pre-snow rainfall condition? How sensitive is shallow flow pass to pre-snow rainfall condition? In general, how sensitive they are to climate variability from year to year. That was what was quantified by mu. Here is our result. So note that in this slide, values in the pie chart actually show the portion of the snowmelt that becomes each flow pass or storage. This is a result for a Nanika watershed, the first watershed that I showed. And we can see that during rainfall poor years, where fall season rainfall is pretty much low, 58% of subsequent snow season snowmelt become shallow flow pass, and 4% become long-term storage. However, during rainfall-rich years, where fall season rainfall is pretty much high, only 47% of subsequent snowmelt become shallow flow pass, and 25% of subsequent snowmelt become long-term storage. So we can see significant time variance in a snowmelt partitioning pattern between rainfall poor year versus rainfall rich year. Let's look at the second watershed, creekland watershed. Generally, snowmelt partitioning pattern are pretty much similar, and we don't see significant differences from rainfall poor year to rainfall rich year. Just to remind you, the first watershed was the one with laterally heterogeneous subsurface property, and the second one was the one with the laterally homogeneous subsurface property. The same variation in climate signal produces different extent of functional time variance in two watersheds. Laterally heterogeneous Nanika is highly temporally variable. Laterally homogeneous creekland is relatively stable in terms of the snowmelt partitioning pattern. And we know that the snowmelt partitioning pattern here is a proxy for watershed hydrologic function. So of course, with two watersheds, we cannot generalize these findings, but we know that there are three factors that change between these two watersheds. First, watershed topography or slope. Second, the extent of vertical heterogeneity in permeability. And third, the extent of lateral heterogeneity in permeability. Therefore, we design visual experimentation to isolate the role of each factors and systematically assess how each of these factors mediating the snowmelt partitioning sensitivity to pre-snow rainfall condition. If you heard about interaction in a statistic, it's exactly that interaction, how physical properties of landscape change the sensitivity to climate. And as I explain in the next couple of slides, we can understand this in more detail. A slope and extent of vertical structure strongly control flow path pattern. This is what we expected. They control flow path pattern. However, they are not modulating the sensitivity of a snowmelt partitioning to pre-snow rainfall condition. What does it mean? It means that flat and steep watershed, everything else the same, remain almost equally sensitive to pre-snow rainfall variation. The same for extent of vertical contrast in conductivity. Increasing vertical contrast in conductivity did not affect the watershed functions or snowmelt partitioning pattern sensitivity to pre-snow rainfall condition. But lateral heterogeneity strongly modulates climate-induced functional time variance, or strongly modulate climate-induced snowmelt partitioning pattern, where we systematically increase lateral heterogeneity in the subsurface from fully homogeneous system to a strongly laterally heterogeneous system. The time variance of a snowmelt partitioning pattern or watershed hydrologic function significantly increased. Here, the y-axis, mu+1, reflects the climate-induced sensitivity of snowmelt partitioning to pre-snow rainfall condition. For a fully homogeneous system like this system, we can see minimum sensitivity of the snowmelt partitioning pattern to pre-snow rainfall condition. So pre-snow rainfall condition, actually for this type of system, fully homogeneous system, we can see minimum sensitivity of a snowmelt partitioning to pre-snow rainfall condition, like creekland watershed. The system which was laterally homogeneous, its sensitivity of watershed function to pre-snow rainfall condition to the one of the major driver of climate variability in these sites were almost actually very least sensitive, or the snowmelt partitioning pattern were very similar during rainfall poor years versus rainfall rich year. However, as we go toward a strongly laterally heterogeneous system like this system, we can see that particularly the time variance of a snowmelt contribution to long-term storage increased by more than 600 times. Indeed, in laterally heterogeneous watershed, a snow-fed flow path pattern, and in particular a snowmelt contribution to long-term storage, strongly depend on pre-snow rainfall condition. Indeed, lateral heterogeneity is the modulating force that controls whether a watershed function is stable or wildly sensitive to variation in climate condition. If you are interested to learn more about this or read more about the science and physics behind this result that I presented in this study, please read this piece that I wrote for Phys.org about this paper. Overall, these results show that climate variability interacting with a lateral heterogeneity is a physically plausible candidate mechanism for functional time variance. The second study of this part actually focuses on one of the most complex landscapes that I work on, prairie pothole region, with 5 to 8 million glacially carved wetlands, and it's an example of actually wetland-dominated landscapes. The motivation of this work was that in most annual water balance framework, such as extension of Budico framework, Budico framework generally used for actually a spatial analysis from one watershed to the other. But the extension of Budico framework was used to evaluate how water cycle and a runoff response actually change from one year to the other. In most annual water balance frameworks, such as extension of Budico, year-to-year runoff variability is a direct translation of variability in watershed scale climate drivers, including these drivers that I'm showing. These are the drivers that used in previous studies that showed that they are strongly controlling year-to-year variability of runoff ratios. Annual aridity index, annual snow persistence. Snow persistence shows how long snow remain on the ground in each year. Is it remain on the ground until June or remain on the ground until March, April? Annual rainfall maximum, annual climate seasonality, and annual net water input or annual maximum net water input. In this study, our objective was to evaluate, is it climate variability or landscape features here, wetlands, that set year-to-year variability in runoff ratio? And our method was partial correlation to isolate the effect of annual watershed scale climate indices versus annual wetland inundation index. The data that we used was 38 years of precipitation stream flow observation along more than 100 non-regulated watersheds. And we also used satellite data on wetland inundation and satellite data on snow presence on the ground. Here is our result. Partial correlational analysis showed that interannual variability in wetland inundation extent explain year-to-year variability in runoff ratio more strongly than any watershed scale annual climate indices that we used, along close to 70% of study watershed in prairie pothole region. These watersheds were shown by red dots and was labeled as field spill dominated watershed. Let me evaluate the mechanism of this type of watershed through an example watershed in North Dakota. In this figure, x-axis shows the annual wetland inundation percentage, the percentage of the whole watershed that's being reflected as a wetland, inundated wetland in each year. And the y-axis shows the annual runoff ratio. Each dot refers to 1 year out of 8 years of available data record. During the years that annual wetland inundation was small, so this is just one watershed, we are evaluating just one watershed here. During years that annual wetland inundation was low, below a threshold of close to 3%, the years that we call them field phase dominates, climate inputs actually are trapped as storage, and wetlands show minimum connectivity with small runoff ratios. You can see cluster of very small runoff ratios here below the threshold of 3%. However, once in the years that wetland inundation passed the 3% threshold, 3.2% threshold, the years that we call them spill phase dominance, inundation exceeds critical storage and wetland hydrologic connectivity and runoff ratio disproportionately actually expanded. Indeed, annual wetland inundation extent serves as a proxy for annual storage states, and it tells us whether the system is filling or spilling phase in a given year. That's why we call this type of watershed as field spill dominated system. But field spill domination process is a very well established actually process at the event scale, at the daily scale in prairie pothole region. But here we are showing that it's also valid and strong enough, stronger than climatic signal, even at the annual scale. The next question is that what controls the strength of functional nonlinearity between wetland inundation and runoff ratio that I showed in the previous slide? And the answer is the extent of geographically isolated wetlands. Geographically isolated wetlands are the wetlands with no permanent surface connection to rivers, lakes, or stream, and they feel and spill independently. In answer to that question, we fitted the Power law relationship to each watershed, wetland inundation and runoff ratios, with parameter B of the Power law or Power law component captured the degree of nonlinearity. Higher B referred to a stronger threshold behavior, like what you see here in this system, and also a stronger time-variant watershed hydrologic function. And lower B close to 1 referred to linear system. So a Spearman correlation between the extent of geographically isolated wetland and Power law parameter B, once we quantify the correlation spatially from watershed to watershed, was 65%. And this was the correlation way higher than the correlation between 10 or 12 other physical factors with respect to B. So extent of geographically isolated wetlands strongly controls the nonlinearity of this curve. The key insight is that more geographically isolated wetlands are actually corresponding to more distributed storage that must fill before a spillage happen. And this creates a stronger threshold behavior and functional time variance. If you are interested in policy, these gives are highly vulnerable to policy change and being removed, specifically in Alberta. If you have heard about Alberta wetland policy, which was implemented from March 11, 2026, just less than 1 month ago or 1 month ago. So all these gives are now allowed to be removed by farmers based on that policy. And we can show that, we can see that how these gives control the watershed function and time variance of the watershed function. This slide shows two real, watershed in prairie plateau region. We can see this watershed, which we call them linear responder, with B very close to 1 and gives extent of less than 1%. But on the other hand, we can see a watershed, which we can call them extreme buffer or extreme threshold-like behavior, and B equal to 6. And you can see that the gives extent is just slightly larger than 3%. So even a modest 3% gives footprint creates a massive threshold effect at the annual scale. And 3% means 3% of the watershed, so it's almost nothing, but you can see its footprint can be disproportionate. Getting back to the main question of this section, what drives functional simplicity or time invariance and functional complexity or time variance? In the first part, hill slope dominated landscape, I showed that subsurface lateral heterogeneity modulates functional time variance. And the second part, wetland dominated landscape, I showed that wetland extent and inundation patterns drive functional time variance. Landscape structure, not just watershed scale climate summaries, set the pace of runoff or annual runoff and drives functional complexity or time variance. Getting back to one of the slides that we saw before, now we can understand the rationale behind this box plot. Here I showed that HPV lump model performance, predictive performance, significantly decreases as we go from simple watershed to our complex watershed. And we know that simple watershed reflect time invariance behavior and complex watershed reflect time variance behavior. Now we know one of or two or some of the causes of functional time variance. And that's the spatial heterogeneity in the watershed. That's the landscape feature that are spatially distributed. But HPV lump model cannot incorporate all these spatial heterogeneity, which are the main causes of time variance. And no level of optimization or better calibration or better optimization tool cannot compensate for this structural mismatch. The reality of the watershed versus what we model or the structure of the model that we select and we use. Now let's turn to seeing how understanding of watershed hydrologic function can inform deep learning model development and model evaluation. If most watersheds exhibit functional complexity or time variance, and if landscape structure and heterogeneity drive this complexity and time variance, the question is that can process agnostic, especially long deep learning model reliably capture this prevalent functional complexity, or do they learn simplified pattern from lump inputs that cannot represent the underlying spatial processes? The analysis that I showed here was conducted by my current PhD student, Ara Bayati, and my current PhD student, Jawad Rahmani. Okay, I'm in Waterloo, and I cannot actually criticize AI that much, and I have to say that deep learning models, particularly LSTMs, are the current champions of rainfall runoff modeling. We have to acknowledge that. And across more than 1,000 watersheds in North America, we showed that median tested NSE of 0.75 and median tested KG of 0.81. This is unprecedented goodness of fit, and I don't call it predictive accuracy, but I can call it preciseness. It's a perfect goodness of fit that we cannot achieve with any other model. However, we do not know how they predict stream flow. Deep learning model such as LSTM, they take some daily inputs such as precipitation, temperature, and sometimes PET, in addition to a long list of physical attributes, and then they generate a stream flow. However, the internal functioning f of t remains black box. And this actually motivates the central questions of our talk today, functional realism. The extent to which a model's internal functioning aligns with defensible hydrologic function. And in answering to this question, we extracted the internal functioning of LSTM for those watersheds with exceptional goodness of fit. So for only those watersheds with KG and NSC during test set of larger than 70%, we are going to extract the internal functioning and see what they learned. The toolbox that we used to extract the internal functioning of LSTM was LSTM IRF. This is a hydrology-specific XAI framework that we developed, and this uses a neural network. This uses a neural network to extract impulse response functions, impulse response function, or time-varying unit hydrograph, actually that LSTM learned to simulate a stream flow. Indeed, in each watershed, we developed two models. One original LSTM model that we want to evaluate its internal functioning, and the second one, XAI surrogate model that tried to replicate the original LSTM model and learn what was the internal functioning that LSTM learns to simulate actually a stream flow. The XAI surrogate model was able to replicate the LSTM behavior with high accuracy with the median NSE of 0.84, and that XAI framework also able to isolate the net lag contribution of precipitation, temperature, and PET to simulated stream flow. Before I show you how reliable are LSTMs, let me set a priori expectation against which we evaluate the functional realism for rain-dominated watersheds. Time-varying IRF, so from now I call impulse response functions as IRF. Time-varying IRFs show the net effect of a unit change in each climatic variable on a stream flow at different times of the year. And by net effect, I mean we already adjusted for potential correlation among all climatic variables. So generally, time-varying IRFs show the net effect of a unit change in each climate variable on a stream flow at different times of the year. So we can have a daily IRF. And instead of showing all daily IRF here, I'm showing the ensemble of all daily IRFs here. So our expectation of ensemble of daily IRF or ensemble of IRF for precipitation is something like this shape. Why? Because rain adds water and stream flow should increase in response to a unit impulse of rainfall, and therefore we expect a positive IRF. This is the hydrology 101, right? That's the unit hydrograph. How about our expectation of IRF of temperature? In rain-dominated system, heat primarily evaporate water, so flow should decrease or remain neutral in response to a unit increase in temperature. So we expect this shape for IRF of temperature. And finally, PET. PET is evaporative demand and removes water, so flow should decreases with negative IRF. This is what we expect from PET. PET always take out water, so we don't expect zero or positive IRF shape for potential evapotranspiration. Let's look at the results through an example of rain-dominated watershed, and note that this rain-dominated watershed was labeled as complex time variant in our previous analysis that I showed at the beginning of the talk. And here I'm showing the IRF of temperature. We can see that temperature rise corresponds to a stream flow generation without rainfall. I'm saying without rainfall because this is the net effect of temperature. We already adjusted for the effect of precipitation and PET. So think about heat wave, think about extreme heat wave. So this model, if extreme heat wave happens without any rainfall, is going to generate significant amount of stream flow. Also, as I told you, so here I'm showing the ensemble of IRF, but we have all daily IRF, so we can quantify the standard deviation of the IRF over time. So, and if a system is time variant, we expect very large standard deviation of IRF from time to time. But however, as you can see here, the standard deviation of IRF shown in gray in this figure is much smaller than the average of IRF that we can see here. So this system or the model did not learn a strongly time variant functional behavior of this system between P and actually time lag. This is the IRF of precipitation. So what was the KG of the model over tested? The KG, LSTM's KG of the model was 0.91. This is very strong KG, but we can see that exceptional goodness of fit masks physically implausible behavior in a learn relationship. This pattern was prevalent across North America. Blue color in this figure shows watershed wherein 1 to 3 days of temperature increase corresponds to a stream flow increases without additional rainfall, and you can see it's almost everywhere. So in the blue area, if we use perfect LSTM model, and if you are going to model the effect of heat wave, we can expect that significant stream flow being generated as a result to heat wave. This is something that we call heat wave hallucination. Let's see our expectation, our prior expectation against which we evaluate functional realism in a snow-dominated watershed. The first figure shows IRF of P, and we know that precipitation still adds water, so we expect positive IRF. Temperature or heat here melts the snow, so flow should increase and IRF should be positive. Indeed, a unit pulse of temperature may correspond to a stream flow increase. So this is our expected IRF of temperature in a snow-dominated watershed. And finally, PET. PET still removes water and removes water through evaporative demand, and therefore it should decrease actually a stream flow. So the response to pulse of potential evapotranspiration should have like a negative shape, as we see here. Let's look at the result through an example, a snow-dominated watershed, and this is the IRF of PET. And you can see how much these values are large. PET melts a snow heavier than temperature. I didn't show IRF of temperature here for the sake of space. PET melts the snow heavier than temperature and generates a stream flow stronger than P. You can see P and PET both have the same unit, and you can see how much the values of PET are larger than the values of IRF of P, specifically along the short lags. But PET is evaporative demand, and it removes water. It doesn't melt snow and should not show positive IRF. So this is what we don't expect. We don't expect positive IRF for PET. And getting back to KG, the LST and KGO were tested was 84%, which was really high. Again, this behavior is widespread across US and Canada. Blue color shows watershed where in 1 to 3 days of unit PET increase correspond to a stream flow increase without a change in precipitation and temperature. Specifically along the Rocky Mountain, this is very problematic. This means that if PET increases, but T doesn't increases or change, so because PET includes like a wind, a humidity, radiation, so but if PET changes, but T doesn't change that much, so along the Rocky Mountain, this perfect model can lead to larger stream flow generation just because of PET change. But why does deep learning learn this spurious correlation? The answer is simplicity bias. Deep learning actually takes the path of least resistance. Deep learning takes the path of least resistance that I'm showing here and prefers simple statistical links over complex time variable physical chains. In computer science and large language model, simplicity bias is very useful because they have access to billions of data and they leverage simplicity bias for generalization. This is very important. Still, they are working on that to reduce it and fix it. But for example, if you work with chatbots, you can compare ChatGPT and Claude AI, right? So ChatGPT generalized much better. Claude AI is more, it kind of narrowed down because they try to reduce the simplicity bias in Claude AI. But in hydrology, we don't have access to significant amounts of data like large language models. And we believe that the nature of data in hydrology and the pre-processing that deep learning hydrologists do before starting to develop deep learning model may facilitate simplicity bias. The first one, which is about the nature of data, is seasonality. The model confuses seasonal coincidence with causality. Snow melts in mid-spring when PET starts to increase, or temperature co-varies with the stream flow in rain-dominated systems. So in many watersheds, when PET starts to increase, is the time that the stream flow starts to being generated. And because PET signal and temperature signal are very smooth, model deep learning loves a smooth signal in the input data because it can identify and extract very good relationship. By very good, I mean in terms of goodness of fit, right? It can make very beautiful goodness of fit if it uses a simple, smooth signal of PET or temperature instead of highly fluctuated signal of precipitation. So seasonality of input is might be a key factor that cause simplicity bias to happen in both snow-dominated and rain-dominated watershed. The second thing is about pre-processing. And those who work with deep learning know that the best practice is to merge rain and snow-dominated watershed as well as rain and snow-dominated events during training, and this is helpful for generalization, right? But this may create confused internal logic. This spatial merging may generate a confused internal logic because rain-dominated watershed may learn that if actually temperature increases, they have to generate a stream flow because they learned it from a snow-dominated watershed, right? This spatial extrapolation in data can be critical. And the last one is absence of causal driver. In current deep learning approach, we don't include lateral heterogeneity. We don't include field dynamic. And we know these factors cause functional time variance and cause functional complexity. These are the real driver of time variance, but they are not in input data. And the model substitute this complexity with spurious proxies, such as a simple relationship between temperature and PET and stream flow. Long deep learning models are compensating for unobserved spatial processes that drive functional time variance by learning simple time variance proxy relationship. Physics-informed hybrid model to a large extent reduce simplicity bias. Think about the deadlock of hydrologic modeling, prairie pothole region. very complex region to predict. And previous AI and conceptual hydrology model and also plain LSTM model failed to simulate hydrology of PPR. In a very recent work, we tried to incorporate field physics within a body of a model such as HVV or a process model. Field physics was incorporated in a pothole module as a pothole module within a body of like a simple process-based model, and just let the LSTM to learn and regionalize the parameters of this system. This is called hybrid deep learning model, that we use a core of process-based model, and we use LSTM or any type of neural network to learn parameters and extrapolate parameters to the engaged region. So in general, we leverage LSTM effectiveness in parameter optimization and regionalization, plus a better process realism and incorporation of lateral heterogeneity. Field physics and lateral heterogeneity that is important for functional time variance was incorporated through this pothole module. The performance was satisfactory, so stream flow actually regionalization specifically to engaged basin was satisfactory, and compared to plain LSTM, we got almost twice the median KGE. So it changed from 37% KGE to something around 55–60% KGE in prairie pothole region. But beyond that, what was very interesting for us was the regionalization of pothole water storage dynamic. And this was predicted and validated against satellite-based estimates. And then we were able to regionalize pothole storage water dynamic to engaged landscape. This figure actually compared the simulated pothole storage versus observed inundated area percentage that obtained through satellite data. And this is over different years, and this is in one watershed. So we can see that in this watershed, there is a perfect correlation of 81%, which the watershed that we treated as engaged, that we can see there is a perfect correlation between simulated pothole water storage and what satellite data tells us in terms of variation of pothole storage along the watershed. So the lesson that we learned through this hybrid modeling was that embedding the region-specific processes, we embedded the prairie pothole-specific processes in the body of LSTMs directly into the model structure enables regionalization to engage landscape. And this reminds me of one of our previous work in 2021 that we showed that even using simple regression, random forest, XGBoost, or classification approach, even using this approach, if we use functional indices that reflect the storage, release, and partitioning of the water, if we use these indices as inputs to this traditional machine learning model, we can strongly and significantly enhance the regionalization capability to engage and poorly gauge region. So hybrid modeling are expanding fast. So these are two examples of them. Delta HVV or differentiable HVV or mass conserving perceptron approach. But the key frontier is not model training or optimization anymore. The key frontier is a structural design, because we have a wide variety of structural choices to select in this hybrid model. Storage architecture choices, number of buckets in Delta HVV, parameterization choices. We can have a static versus time variable parameter in hybrid model, which is a very useful actually a strategy. Spatial choices, we can have lump versus multi-sub-basin distributed hybrids in Delta HVV. Or in mass conserving architecture, we can select among these different architecture. But currently, there is no strong tool to select which structural design we have to select for our model. An optimal structure is often selected based on marginal KG and NSE gain. But marginal improvement in KG and NSE may have little correspondence to improvement in functional realism. Oh, I'm done. Just one slide. So, I suggest that design and evaluation of a structural complexity should be complemented by observation-based functional guidance, so the structure is chosen for functional realism, not just better KG and scores. And this is actually the last slide of my talk that shows that the observation-based functional guidance can be used for both model development and validation. Think about that functional classification that I discussed at the very beginning, simple, intermediate, and complex which reflects functional time variance or time invariance. If we know this classification before we are going to design our model, we can determine if time variance exists in PQ behavior or not. It can guide the number of buckets needed. It can guide time variant versus time invariant parameters. And it informs distributed versus long choice. We can also use LSTM-IRF, the XAI surrogate model that I showed you, on observational data to see how time variant or IRF in observation. And then based on that, we design and we select our structural choices in hybrid, actually deep learning model. These diagnoses can also be used after modeling to evaluate the functional realism of the model in the way that I showed for deep learning. We use these diagnoses such as LSTM-IRF to evaluate if the learning of a hybrid deep learning model or hybrid models in general makes sense, if they are as time variant as what we expected, or if they are as time invariant of what we expected. And this is the last figure of this talk, where I'm trying to convince you that we need actually to have both good goodness of fit or improved goodness of fit, as well as actually functional realism as an additional validity target. And this actually brings me to wrap up a slide. I'm not going to read through that because of the time, but these are the conclusions that we made through this work. Thank you for your attention, and I would be happy to take your questions. Yeah.
Great talk. The question is about that snow melt drive example that you showed, the two scenarios.
Okay, yeah.
You said the snow water equivalent was the same?
Very similar. Yeah, we selected, so generally our goal was to select years that we just isolate fall rainfall condition, but all other factors are very similar.
The question is about how about the snow density? Because if the snow density is different with these scenarios, and then if you get rain over snow, that will change the forecast. Did you consider that?
That's a very good question. So we didn't see the footprint of rain on snow in these two watersheds, but of course, yeah, rain on snow is a very important feature. So generally, we checked both because we had observation of the snow and snow melt in these two watersheds as well. That's why we selected these two watersheds. But we also checked the simulated snow melt using Parflow CLM, and because it uses CLM, and CLM is a land surface model, that simulated snowmelt was also very similar between 2 years. So we expect that density was already incorporated, or probably it's just lack of data, because we had information on a snow water equivalent by Environment Canada, and the watershed in Sweden is a very well-studied watershed for the last 50 years. So we had all this information, but for sure, snow density might be missing, but we trust the model. And because it tells us both snowmelts in both years were very similar. Yeah.
Thank you, Doctor. I really appreciate your presentation. So I have a question about the wetland-dominated catchment.
About what?
Wetland-dominated.
Wetland-dominated.
Yeah. So you concluded the wetland extent and the inundation are the key drivers for the functionality. But what drives the
That's a very good question. Read the paper. Read the paper. Paper is impressed. Paper is impressed in Communication Earth Environment, not officially published, but you can find the impress version. So we significantly evaluate this one, and we saw that among those 70% of watershed that we labeled them as fill spill, a snow persistent to a large extent control wetland inundation. This is a very good question, because people think, okay, inundation is being driven by climate, so we cannot ignore climate still. Note that first we done partial correlation to adjust for all this mutual information. So this was already adjusted. But then we evaluated what controls wetland inundation, and only in, I think, 20% of those fill dominated watershed, snow persistence actually had a good correlation, like a 60%, 55% correlation with wetland inundation extent. So in some of these watersheds, we can assume that, again with correlation, we cannot make any theory or hypothesis, but we can assume that actually wetland inundation extent is being controlled by some climatic features, and here it was snow presence. But what happens in terms of the other watershed, and what happens in terms of the other variability that snow presents, and no other climate driver could explain? We believe that it's all about the spatial heterogeneity of wetland inundation. In the talk, I emphasize on annual climate summaries. So in prairie, we have large watersheds. So when we take average over the entire watershed, we ignore a spatial variability of climate features, which is very important. A spatial variability of snow presence because of the drift wind, So all these factors can create a spatially variable inundation pattern, right? And that spatially inundated pattern can be highly decoupled from watershed scale annual climate summaries, right? It also might be the effect of previous year's climate. So water that's coming from groundwater that current year annual climate summaries could not explain. Whatever is the control of wetland inundation that we don't know what exactly those control, or at least among the list of check the paper, I think we evaluated more than 12 climatic features, both intra-annual climatic, inter-annual climatic features, and none of them were controlling actually wetland inundation extent, except snow persistent in some of the catchments, in some of the watersheds. So whatever controls, we now have the wetland inundation extent that can control runoff ratio, So, and as I said, it's mainly because of the heterogeneity of the climate features, sources of water that's coming from previous years or years before, and dependent on like a 2 years ago, 3 years ago climate, So, but at the end of the day, what matters is wetland inundation that strongly controls runoff ratio.
Thank you. So I'm actually going to cut us off here because we're past the hour and I wasn't doing my job and wasn't watching the clock. If you have any additional questions, Ollie's around. He's willing to talk to people one-on-one, so come up front, but the rest of you are allowed to leave. Sorry, I should have discussed.
Before you walk out, thanks very much to the speaker. Of course, thanks all for joining us. Just a very short announcement. In 2 weeks' time, on the 1st of May, we have a distinguished lecture by Professor David Sedlak from the University of California. He's a distinguished lecturer in the Association of Environmental Engineering and Science Professors event in Canada. And we're very proud and very happy to be able to host it here at the University of Waterloo campus. So the talk is on the 1st of May. Register on the Water Institute website, please. It's going to be a great event. He's an amazing person. You may have heard of him. He's going to talk about nature-based treatment to solve the global water crisis. So it's going to be an exciting event. There are going to be snacks and everything else involved as well. So a lot of incentive, I hope, for you to register. I hope to see you all there. Thanks very much. Thanks.
Thank you.